Okay, good afternoon. A couple of minutes late. Um, Two example problems you have to get to today, and then we are done. We are done with all the material that we need to cover. All 7 chapters are done. AC power is the last topic for today, and then the last um, quiz will be on Monday on AC power. I'll give, I don't know, 40 minutes, 45 minutes, however you need, however long you need. Um, and then there will not be any class after that. That's it. You're done. Then I'll see you straight on the day of the final. So let's get to it. Yes. No, just open office hours. If you have questions, just come by. I'll be here. I'll be on campus in my office. Yeah. And I'll talk more about that on Monday. Yeah. So let's see. Sorry. No, no attendance. All right. I think we had stopped here talking about power triangles for capacitors and for inductors. So if you have a RL circuit, you have a resistor and you have a inductor in the same circuit, then some of the power is diverted to the resistor, some of the power is the reactance reactance of the inductor. So that would be noted by QL. Resistive power is P, should not be L actually. Resistive power or real power or average power is simply noted as P. And then reactive power for inductor is noted as QL. Reactive power for capacitor is noted as QC. Now, in a inductor, voltage always leads the current, right? So current is lagging. So current lags the inductor by 90 degrees. So the impedance angle for an inductor and hence the power angle for an inductor is always plus 90. So QL is always pointing straight up. In a capacitor, it's the opposite. In a capacitor, the current leads the voltage. Or in other words, voltage is lagging by 90 degrees. So the impedance angle for a capacitor and hence the power angle for a capacitor is always minus 90, meaning QC is always pointing straight down. Okay, and that's what we see in this power triangle. Okay. And from this, we can define a couple of new terms. Power factor. Power factor is typically expressed in percentage and is actually calculated as the cosine of the power angle. So cos theta gives us the power factor. The reason, of course, is here. We want to minimize this. We want to minimize the reactive power that is required in a system because the reactive power is not doing any real work. Okay? It's not doing any real work. How many of you are over 21? I wanted to make a alcohol reference. You may have seen images. I would not say that you're going to a bar, but you have seen images of a beer mug with full of beer with foam at the top, right? Reactive power is like that foam. Anyway, I will not say more than that. All right, so we have inductive reactive power, capacitive reactive power, and the goal is going to minimize that because it's not doing any real work. So if we make that smaller, what happens to that power angle? It becomes smaller, right? It becomes smaller. So cosine of the power angle, the power factor is important in terms of AC power. If theta is equal to 0 in an ideal system, so the ideal value of theta would be equal to 0. Cosine of 0 would be equal to 1. Power factor is expressed as a percentage, and we would say power factor is equal to 100% because the angle reactive power is equal to 0. This is the highest possible value. Okay, this is the highest possible value. Also, we express power factor as either lagging or leading. This is expressed from the reference point of the current. If the current lags the voltage, we say power factor is lagging. If the current leads the voltage, we say power factor is leading. Okay. So again, the reference point is voltage and our perspective is from the current. Current always lags in an inductor and always leads in a capacitor. Okay, so power factor for an inductive system is always lagging. Power factor for a capacitive system is always leading. All right. Now you may have noticed in the power triangle, you had P, you had Q, and you have the hypotenuse of a right angle triangle, which is the product of the voltage and the current, specifically the RMS value or the effective value of the voltage and current. This value is termed as the apparent power, which is the magnitude of S, the total complex power. S, of course, is the total of P and Q. S is equal to P plus JQ. It's the total of P and Q, right? Mathematically represented P plus JQ. So when we convert this into polar coordinates, you get magnitude of S and you get the phase angle theta. Okay. So apparent power is the magnitude of S given by the product of voltage and current. The unit is volt amperes, VA. Total complex power has a unit of volt ampere, hence magnitude of the complex power is also VA, volt ampere. Some other equations, S can also be determined by this equation, half times the product of V and I conjugate. These are phasors. So phasor form of the voltage and phasor form of the current gives you the total complex power, or twice the complex power. Okay. This asterisk, as you see over here, don't need an arrow. This asterisk notes that this is the complex conjugate of I. Complex conjugate of I. Complex conjugate of any complex number is simply the point in the plane that is in the opposite quadrant. So A plus JB would be equal to A minus JB. R with a phase angle theta would be R with a phase angle of minus theta. So product of V times the complex conjugate of I. Equations for the resistor are still the same. You have seen this before. P is equal to I squared times R, or V squared over R. Reactive power Q, you can use I squared times X or V squared over X. Okay. And X, of course, is the reactance of that component, whether it's an inductor or whether it's a capacitor. All right. Okay. Let's get to our example. All right. Example 1, we have a circuit. Let's remove these notations for now. We have this circuit, and we are asked to find the power for every single component, which means how many components do we see on here, by the way? 3, actually 4. You also have to find it for the source. If it says every single, that means every single component source will also be a component of that circuit. We have to find the power for every single component, means we have to find the power for all 4 of them. All right, so first, if you want to solve this, we need to have either the voltage or the current, right? Let's say we just take the resistor. If you want to find the power for a resistor, what do we need? We need either the voltage or the current. If we have the voltage across the resistor, we can do V squared over R. If we have the current through the resistor, we can have I squared times R and determine the power that way. So we need the same thing for the inductor, we need the same thing for the capacitor. No difference. Okay, no difference. So to solve this, well, first we need to determine the voltages and currents across each of these. Okay, so let's work from the top down in that sense. Here, power for the resistor, power for the resistor. What do we need? Voltage, or we need the current? For the inductor, again, the inductor voltage, capacitor, we need the capacitor voltage, or alternatively, we can solve with current for the inductor and current for the capacitor. If we wish to find the voltage, let's say it's a 3 resistor circuit, what do? We reduce everything down to one single resistance, apply Ohm's law, find the total current, and then expand it back up again. So that's what we're going to do here. First, I'm going to draw the equivalent impedance diagram. Chapter 5, AC analysis. Equivalent impedance diagram means I have everything replaced with its complex quantity. Voltage source Vs is represented as a phasor for Vs. We have current I coming from the source. IL, the inductor current, would be the same as the total current I. Current coming down here can be labeled as IR. Current coming down here can be labeled as IC. If I apply KCL at the top, I obtain total current I is equal to IR plus IC. So there are many avenues we can use to determine the current. We can apply series parallel equivalent analysis, meaning finding one single ZEQ, apply Ohm's law, and then expand the circuit. Or we can apply voltage division, or we can apply current division. Any one of those is fine, whatever you choose. Okay, let's do ZEQ. Equivalent impedance diagram. ZL and ZC replace the inductor and capacitor. R and ZC are in parallel. Combine them to form ZRC. Right now, I'm not performing any calculations, right? I'm simply setting it up, right? So I form ZRC. Then ZEQ would simply be ZL plus ZRC. Let's take a pause. Let me know if you have any questions so far. So far, so good. Okay. All right. So ZEQ is ZL plus ZRC. Now I need to find what ZRC is, and I need to find what ZL is. So AC analysis. Phasor for Vs, well, obtain magnitude 10, phase angle minus 90. So Vs is 10 with an angle of minus 90. ZL is J omega L or omega L with an angle of plus 90. So J times 1000 times 0.1, J100 or 100 with an angle of 90. ZC is 1 over J omega C. So minus 1 over J is minus J. So minus J over 1000 times 10 microfarads gives me minus J100 or 100 with an angle of minus 90. 1 over omega C with an angle of minus 90. Both rectangular coordinates as well as polar coordinates. ZRC is R in parallel with ZC. R in parallel with ZC gives me R times ZC divided by R plus ZC. We solve that and obtain 70.71 with an angle of minus 45. At the same time, I'm also determined to find, not determined, I'm also want to find the rectangular coordinates. That's 50 minus J50. Now, you could obviously do this and program all one single equation into your calculators if you can. The only thing is you should be an expert at programming your devices. Because if you make one simple error somewhere in entering the equation, your entire calculation or final answer would be incorrect. Okay, so you need to be careful about that. All right, so that is ZRC. So my total ZEQ, ZL plus ZRC, J100 plus 50 minus J50 gives me a total ZEQ of 50 plus J50 ohms. Polar coordinates 70.71 with an angle of 45. Because I need to perform a division, I'm going to apply Ohm's law in the next step. So walk with me. We have a circuit. We have 3 components in there. There's 3 impedances. Trying. All I've done so far is find ZEQ, reduce the entire circuit down to one single impedance, so I can apply Ohm's law and determine the total current that is flowing in that circuit. Okay, so I have my ZEQ here. I apply Ohm's law here, and I obtain my current right there. 0.1414 with an angle of minus 135. This one? This one? Oh, ZRC here. The only reason I did that is because I wanted to perform the summation. The question being asked is, why did we do rectangular coordinates after determining the answer in polar coordinates? If your calculators can add 70.71 with an angle of minus 45 plus J100, then you can just program it directly. I needed to perform this addition, so I needed these coordinates. That's why. Okay. All right. Let's see. Oh, so we found the total current I. Okay, so total current I is 0.1414 times minus 135. Okay. This 0.1414 only gives me the magnitude of the current. It is only IM. IM. To find IRMS value, I have to divide it by root 2. Okay, divide 0.1414 with root 2. Right now, I don't need it, so I'm just letting it be. VR and VC are the same because they are in parallel. If I find the current I, the total current I flowing through ZRC, the parallel combination of R and C, I have that voltage, VRC. Okay, so VRC is Vs times ZRC over ZEQ, or I times ZRC. You can try and do both. You should be able to obtain the same answer using both equations. Okay, I have two impedances in series, ZL and ZRC. This diagram right here. Okay, R and ZC are combined to form one single equivalent impedance. I have the same current I flowing through the entire circuit, causes a voltage drop across ZL, causes a voltage drop across ZRC. I can apply Ohm's law to inductor, find VL. I can apply Ohm's law to ZRC, find VRC. Or I can apply voltage division, VS, ZL, and ZRC. And I can find the voltage VRC. Either ways. The techniques that we are using here are no different than what we did earlier in chapter 2. Okay, they're still the same techniques. Only the math is using complex numbers. And these techniques, these DC analysis techniques, will be assessed on the final. So every student needs to be comfortable with these techniques. All right, so by voltage division, find VRC, 10 with an angle of minus 180. IR, VRC over R, gives me a value of 0.1. IC, 0.1 with an angle of minus 90. Once I have those currents, again, remember, I already have the total current for the circuit. The total current is also the current flowing to the inductor. So I have the three currents flowing through that circuit. Once I have the three currents, all I need to do is perform this calculation. I squared times R and I squared times X. And I have my power. Okay. On the left, we see V squared or R, 0.5 watts. On the right, it's I squared times R, again, 0.5 watts. So in the quiz or in the exam, you can choose either the equation on the left or the equation on the right. Both should give you the same answer. Okay, you can pick and choose which one you want to use. That's up to you as an engineer. QL is IL square times XL. 1 VAR. QC is IC square times XC. See, minus 0.5 VAR. Okay, you can perform this with V square or XC. You still get the same minus 0.5 VAR. I haven't solved this. I will assign this as student practice. You should be able to obtain this answer, 1 VAR. Find the voltage across the inductor, and you should be able to apply the power equation and solve it. Okay. All right, let's take a pause. Let me know if you have any questions. I'm again summarizing the steps. Okay. Think back to chapter 2. We had resistive circuit analysis. If Vs was a DC voltage source, what would you do? If it was a DC voltage source, we would calculate either the voltage or the current across these three resistances or three impedances, and then apply the power equation, which is V squared or R or I squared times R. That is all we have done. There's nothing else. Okay. DC circuit analysis, find the voltage or the current for the components, and apply the power equation, V squared over R or I squared times R, except it's in complex numbers. Okay. Now, since we have the power for the three components, we add up all together and we'd have our actual power coming from the source. 0.5 is the real power, PR, and total Q is 1 minus 0.5. So total power, total reactive power is 1 minus 0.5, so 0.5 VAR. The inductor requires 1 VAR of power or reactive power, and the capacitor is supplying half of that. So total reactive power required from the source is only 0.5 plus J 0.5 VA. Does everybody see that? One other way of determining the total power S is by using the power angles. Total power S can be defined as the real component PS and the reactive component QS. Power angle would be theta V minus theta I. Theta V was minus 90 degrees. Theta I we found was minus 135. So the actual power angle is 45. If the actual power angle is 45, total power for the source, VRMS times IRMS cosine theta, gives me 0.5 watts. Total reactive power for the source, VRMS IRMS times sine theta, gives me 0.5 VAR. And again, I obtain the exact same answer, 0.5 plus J 0.5. If the question was simply find the total power supplied by the source, we would not do any of the above analysis. We would only do this, and that's it. Okay. If I was to draw a power triangle for the source, what would I have? I would have 0.5 watts on the x-axis, 0.5 VAR on the y-axis, and then magnitude of S joining them together. And then theta, of course, has to be 45 because both of them are of equal length. QL is 1 VAR. So without the capacitor, your magnitude of S, total complex power, would be far higher. But QC brings it down by half. And so actual power triangle is right here. Okay. One other way of finding S is using the equation half VI conjugate. Phasor for V, complex conjugate of I, multiplied together, and you obtain the exact same equation. Okay. We still need to find I for this. We need to calculate the I. I is not given. So we do have to calculate I. Okay. Voltage V was given to us. I was calculated. Okay, so we do have to perform that analysis. Okay, questions? (241). We can choose any of the methods. Yes. In the quiz, I will most likely not ask students to solve through a long analysis. It's because the topic under assessment is AC power, not AC analysis per se. Maybe a small portion might be AC analysis, but other than that, not much. All right, if there are no other questions, then let's do the second example. In example number 2, we are given a system. It's not quite a circuit, it's simply a system. In the system, we are shown that there are two loads, A and B. All we are told about the system is that the source is supplying this voltage. It's a voltage source. Power for A is given as 10 kVA, Power factor is 0.5 leading. For load B, 5 kilowatts with a power factor of 0.7 lagging. And we are asked to draw power triangles for the load, to determine the total complex power for the source, and to draw power triangles for the source. Okay. So let's extract as much information as we can from the given problem. What's the first thing we notice? 10 kVA and then power factor leading. If power factor is leading, what kind of load is it? It's a capacitive load. So power factor is 50%, more likely than not, has resistors and capacitors. Load B is given as 5 kilowatts with a power factor of 0.7 lagging. That means 70%, and it's probably R plus L. Again, lagging power factor indicates it's an inductor. Leading power factor indicates it's a capacitor. Okay, it actually does not matter because you're not drawing a circuit diagram. But 10 kVA, look at the units. What quantity is being referred to? Again, S is equal to P plus JQ. Units for Q is VAR. Unit for P is watts. Unit for S is volt ampere, VA. So more likely than not, this is referring to magnitude of S. 10 kVA refers to the magnitude of S. 5 kilowatts, on the other hand, is indicating resistive power P. Okay, resistive power P. So we can infer that the 10 kVA refers to apparent power. So magnitude of SA is 10 kVA. Power factor is provided as 0.5 leading, means a capacitive load. So the power triangle should look like this. Now in a power triangle, you have 4 quantities. You have real power P, reactive power Q, complex power or magnitude of complex power S, and the power angle theta. Out of those 4 quantities, you need only 2 to calculate the other 2. If you have a bunch of equations, every equation typically has 3 quantities. So if you have 2 quantities out of 4 in the power triangle, you can calculate the other 2. And because power factor is provided, we can calculate the angle, and we know one of the sides of the triangle. Okay. So in A, power factor is 0.5. Cosine of theta is 0.5. That means theta is 60 degrees. If theta is 60 degrees, I can find real power as VRMS, IRMS, cosine of theta. VRMS and IRMS is the apparent power which is given to us, magnitude of S. And so PA is simply magnitude of S times 0.5 cosine of theta, which is 5,000 watts. Reactive power QA is magnitude of S times sine theta. It comes from these equations. Where did it go? These equations right here. Remember, VRMS, IRMS is magnitude of S, which is apparent power. Which is given to us in this problem as 10,000. So then real power P is 10,000 times 0.5 and Q is 10,000 times sine of 60. So 8660.25 VAR. Two unknowns, we solve for both because it's a capacitive load. Q is negative, hence minus 8660. For load B is provided with a power factor of 0.7 lagging. Because it's lagging, it's an inductive load. That means the power triangle should look like this. QB pointing up. 5 kilowatts, meaning resistive power PB is provided. And since power factor is 0.7, cosine of theta is 0.7. So theta is going to be 45.57. We again apply the same equations. We can find the power angle from the power factor. Cos inverse of 0.7 gives me 45.57. Sine theta is 0.714. Of course, I need that for the following equations. Now, here it's not as straightforward because apparent power is unknown, reactive power is unknown. The only quantities I know are theta and real power P. Okay. So, trigonometric identities. If I wish to find, I have one side of the right angle triangle. I have the power angle. I can find QB by determining the tan or tangent of the power angle. So tan theta is going to be Q over P. You can find Q as 5101.02 VAR. Okay, let's take a pause. Think over that. Let me know if you have any questions. Okay. So once you have QB, you can find the apparent power. It's the hypotenuse of a right angle triangle. Square root of P square plus Q square gives you magnitude of S, 7142.86. Now we add it all up. Total power for source would be PS plus JQS. PS for the source is PA plus PB, 10,000 watts. QS is QA plus QB, it's minus 8660 plus 51. So minus 3559.23 VAR. Since the total reactive power in the system is negative, means the power angle is negative. So if I wish to find the power triangle for the source, we determine P, we determine Q, we need this angle. And that can be determined from tan theta. Tan theta would be Q over P, gives us minus 19.59 degrees. And because overall the system has a power factor, there's a negative angle, that means the power factor is leading. If it's a positive angle, then we say power factor is lagging. It's a negative angle, that means it's a capacitive load, so power factor is leading. Total SS is 10,000 minus J, 3559.23. Source power triangle is shown right here. Yes, negative angle means it's capacitor because it's pointing down. If Q, so a question being asked is about the negative angles. So let me show here. So for source A, QA was minus 8660. For source B, QB is 5101. So total reactive power in the system is negative. Negative indicates it's a capacitive load. The negative simply means it's a capacitive load, it's pointing down. Hence, power angle is negative. So if it's a capacitive load, then power factor is leading. If it's an inductive load, then power factor is lagging. And that's all there is to it. Okay. The approach for this problem was, let's go back to the top. Okay. We are asked to find the power triangles for A and B, and then find the total power triangle for the source. Power triangle has four quantities: the three sides of a right angle triangle, P, Q, and S, and then the angle, the power angle. So you have total of four quantities. We need only two quantities to calculate the other two. That is all we have done. That is all we are doing in here. So when power factor is provided to us, we can easily calculate the angle, cos inverse. The cos inverse of 0.5 gives us the power angle. Power angle for A, cos inverse of 0.7 gives us the power angle for load B. Okay. So we are provided with the angle, and we are provided with one side of that right angle triangle. After that, we're simply applying trigonometric identities to determine the other two sides of that triangle. Okay, that's what we did. Now, it's rather simplistic of me to say that that's all we are doing, but the concept, of course, are not easy, especially if you are learning it for the first time. So you will need to read through it, read through both the examples, go through both the solved examples, understand what it is that we're trying to do. But in summary, again, for the first one, what we did was we applied DC resistive analysis techniques, determined either the voltage or the current through the components, and then we applied the power equation. In this one, we are drawing simply off of the power triangles. Power triangles have four quantities: the three sides of the triangle, and then the power angle. So that's four quantities. And two of those quantities are given to us. We are applying trigonometric identities to calculate the other two. And once we have those two, we can draw the complete power triangle for both. And so that's what we did here. And this is for load A, and this is for load B. Okay. There are some comments also I made in there, so it's solved step by step. And then once you have both loads, now we can determine the total power supplied by the source. I'm simply summing it all up. All right, questions? I'm sure there are tons of questions. The homework's due on Sunday, I believe. Last homework 20. Yeah. If you have any questions, feel free to reach out. I can extend it to Monday if you want, but Monday afternoon is the quiz on AC power. If you think you need more time, just let me know. Yeah, you'll open it up yet? Anyone? Not yet. Okay. All right, open it up. There are some questions that will reinforce the basics and the fundamentals, and then there are a few problems that you can solve in there. So go through this example, go through the homework, reach out to me if you have questions. I will be available over the weekend to answer any questions you have. Reach out via email, I can hop onto Zoom if you need. You can get that ironed out. And we have a last quiz, quiz 10 on Monday. And then most likely the quiz will be of either 40. It'll take about 30, 35 minutes to solve it, but I typically tend to give like 40 minutes, just 10 minutes extra time, and then use the last 10 minutes to just go over the final exam. Okay, so that's probably what I'll do. All right, we'll end class here today. This is the end of the quarter. All the topics have been covered, all 7 chapters, everything is done, everything is complete. Final exam has been, the information about the final exam is up on the website since the beginning of the quarter. Those topics in all chapters 1 and 2, I'll take a look at it and update it if I deem it necessary. But everything else on that page is current. Okay, it's updated. All right, we'll talk about it in the last 10 minutes of Monday class.